Hello, and thank you for watching. My name is Mr. Johnson, and this is one of my 20-minute videos. And the topic for this lesson is dangers of radioactivity, which is a GCSE physics topic, and it's part of the radioactivity unit for combined science and for GCSE physics. So I'm just going to share my screen with you, and then we'll get started. Okay. So, dangers of radioactivity then. Basically, by the end of this lesson, what I'm hoping is that you'll understand the dangers of storing and handling radioactive material, and in particular, be able to describe the dangers of ionizing radiation, describe and explain precautions that can be taken to protect from exposure, and explain the difference between contamination and irradiation. So here we go. First off, it helps to recap the idea of what's going on in an atom. Where do the subatomic particles fit into the atom? What's between them? How they're held together? Now, we've talked about different models in the past. You would have discussed this in your own GCSE physics class, and you'll know about early models, the plum pudding model, the Rutherford model, and the adaptations that were made to it for the Bohr model. But as a general idea, the most accepted model is that the protons and neutrons are together in the center of the atom in a place called the nucleus. The electrons whiz around the nucleus in shells at discrete levels or energy levels away from the nucleus. Between the nucleus and the electrons, there's nothing really but empty space. And the electrons are whizzing around in those shells. They don't fly off because between that and the nucleus, there is a force of attraction between the oppositely charged particles, the protons and the electrons, and by the presence of neutron, which is there to prevent the protons and the protons repulsing each other from the nucleus. So, this patient here was a first responder to the Chernobyl nuclear power plant disaster on 26th of April 1986. For those of you that have not heard the story, Chernobyl was a power plant in Russia, and it is the scene of a nuclear reactor explosion. The reactor basically got too hot. The reactor core released an awful amount of heat and exploded. This then meant that a large amount of radioactive material was exploding and sent outwards, as well as the heat and the fire and flames that this generated. The responders ran straight to the scene. They came from nearby towns and nearby cities to help with the emergency services, providing medical aid. And while running into it, they met a large amount of ionizing radiation. This patient shows signs of radiation burns, where his skin has been burned by the radiation and the radioactive particles that rested on it. A large amount of ionizing radiation can then cause tissue damage, such as ridden skin, like radiation burns, but it can also go deeper than that. It can cause effects that aren't seen to the naked eye. Small amounts of ionizing radiation over long periods of time can damage the DNA inside a cell. Now, from biology, going back to your GCSE, this is a mutation. The damage is caused when the DNA, the molecule which controls the instructions that control a cell, is damaged, and that mutation causes the cell to malfunction, and this then can lead to cancer. Gene mutations that occur in gametes, that's your sperm and your egg cells or sex cells, they can be passed on to the next generation through reproduction. However, not all mutations that occur are harmful, and cells are often capable of repairing the damage themselves if the radiation dose is kept low, which is why it's important to monitor and to know the exposure of radiation, which is why people working with radioactive sources, like our X-ray radiographers and our dentists, they tend to wear dosimeters so they can measure their exposure over time to a dose. So, describe two effects of ionizing radiation on the human body. Common question. It's usually one of those things where the wording is very, very important. First thing is radiation burns. You can't just say burns to the skin. That could be caused by a fire or an open flame. You have to say radiation burns. The next thing is DNA damage or mutations leading to cancer. Again, you cannot just say damage or skin damage. You have to specify. So DNA damage or a mutation that leads to cancer. That's our first outcome met. Let's take a look at our second one. So describe and explain precautions that can be taken to protect from exposure to ionizing radiation. Here we go. The intensity of radiation decreases with distance from the source. So any sources of radiation are always handled with tongs. This then increases the distance between the person that's holding them and the radioactive source by the length of the tongues. That might not seem like much. You might think, well, what difference is that going to make? But remember, some of these radioactive sources are alpha emitters, and that distance between the end of the tongs and the handles is enough that the alpha particles lose most of their energy in the air and can't get anywhere near the skin. The risk can also be reduced by not pointing sources at people and storing them in lead-lined containers, because as we've also discovered during the course of our studies in GCSE physics, lead can stop even most gamma ray sources. In hospitals, medical staff working with radioactive sources have their exposure limited in a number of ways, including increasing their distance from the source, shielding the source, and minimizing the time they spend in the presence of sources. Their exposure is also closely monitored using dosimeter badges. In this case, I always like to think of any time that I've had an X-ray and the fact that when I am sat in the chair waiting for the X-ray, the person puts the X-ray camera on the part of the body that they want to scan. And then that person who is wearing a huge blue apron, which is lead lined, walks away from me and behind a wall or an enclosure with a glass frame in it so they can see through, and then takes the photograph. What you probably haven't realized, if you've ever seen this before yourself, is that that lead lined apron's there to protect them from gamma rays, but the wall is made of concrete and it's usually lead lined as well. And by being at a distance behind that wall, they've employed both increasing the distance, shielding themselves, and also the exposure time is minimal. When they take the photograph, the source is literally exposed for the barest minimum of time it takes to expose you to get a picture. And as soon as it's done, it's closed off. That also limits the time that the person working with the source is exposed for, rather than pressing the button, leaving it on, and then pressing the button to turn it off. A bit like the shutter on your camera. Some patients may be exposed to a dose of radiation for medical diagnosis or for treatment, such as detecting and treating cancer. Again, this is only ever done when the benefits are greater than the possible harm the radiation could cause. So, for example, when the benefit of killing a tumor and extending someone's life, making them cancer-free, outweighs the risk of the radiation poisoning that could occur in the time they're being exposed. And at the same time, the absolute minimum possible dose is used. It's not, well, as an analogy, it's better to use the smallest amount of energy to kill the cells that are causing the cancer than it is to use a stupidly high dose and just aim it at them. It's a bit like trying not to, put a nail in the wall using a lump hammer rather than a small hammer. So some of the employed techniques are distance. You can see here we've got the person holding it with tongs and the radiographer there taking the scan of the lady in the background behind a wall at a distance from the source with glass in between so she can see. We've got X-ray shielding. Again, we talk about the wall that provides shielding. The vest that they use or the apron that they use is lead lined. But what most people also forget to mention at this stage is that the actual source is in a container where there's only one exit for the X-rays or for the radioactive sources to escape from. And that shielding around the source means that it can be very unidirectional. You can point it where you need it to go without worrying about it spreading out and affecting anything else. Finally, monitoring. The idea of a dosimeter badge, something that monitors your exposure to radiation, especially if you're working with them on a regular basis, and lets you know that you've not exceeded safe acceptable levels. So, looking at a question that could come up on this, explain how the following precautions reduce exposure to radiation. The first one I'd be looking at is the source. At a distance, the further it's kept from you, the intensity of the radiation decreases with distance, so less radiation can reach the hands. It's the same idea as shining a torch. Any of you who've played with a torch before, you know, if you shine a torch, so it's literally against a wall, a bright white wall or a desk, it's very bright white and the circle of light is very small. But as you move it further and further and further away, the brightness of the light decreases and the circle gets bigger and bigger and bigger. And this because as you move the torch away, it's spreading out over a greater area. So the intensity at a given point has decreased. The next question, why do they use storing sources in lead-lined containers? It's because lead absorbs all three types of radiation. So keeping them in a lead-lined container means that there's less possibility of anyone outside that container being exposed to any of the three types. That's our second point. Third point, explain the difference between contamination and irradiation. So, like we said before, occasionally there's an accident in a nuclear power station which allows radioactive materials to escape into the environment. Accidents such as this can cause a hazard, as they can lead to people being irradiated or contaminated. There's also the problem of nuclear waste. Whenever a power station is generating energy from nuclear fusion, or nuclear fission, should I say, then there's the waste products that are left behind from that. If they're not stored correctly, or if in the early days of nuclear energy use, we stored them without realizing the dangers, then those also can become a problem. It's important to understand that the dangers of radiation from medicine, industry, and power generation are very small compared with many other aspects of our modern lives. However, many people are concerned that accidents happen in power stations and they could happen to them at any time, and as a result, they wouldn't want them anywhere near. This is an example, Lake Karachay. Starting in 1951, the Soviet Union used Karachay as a dumping site for radioactive waste. Now, looking at this, it's one of my favorite questions to my class. Would you drink or go for a swim in this lake? And 9 times out of 10, the answer is always no, hell no. Why would we even think that? Today, this lake has about 4.44 exabecquerels EQB of radioactivity over less than 1 square mile of water. You might sit there and go, well, what does that mean? But the Chernobyl disaster released 0.085 exabecquerels of land contaminated radioactivity. So this is nearly 5 times higher radioactive count than the actual nuclear disaster at Chernobyl. That's how much this is releasing in any given time. So what's going on then? Well, it's leading into this idea of contamination and irradiation. Someone's irradiated when they're exposed to alpha, beta, or gamma, and that happens when they're exposed to it from a nearby radioactive material. As long as that radioactive material does not land or fall or attach itself to the person, when they move away, the irradiation stops. It's a bit like being in a room with a light on. When you move into that room, you are lit up by the light. When you move out that room, the light bulb will stay behind and you are no longer being lit up. And that's the same idea here. We've got our radioactive emitter, and our radioactive emitter is emitting ionizing radiation. When the person moves away, the ionizing radiation is still being emitted by the emitter, but there's nothing on the person, so they are now not being irradiated anymore. The irradiation stopped. Someone becomes contaminated then if they get particles of radioactive material on their skin or inside their body, just like our lake. They will be exposed to the radiation as the unstable isotopes in the material decay, and this then continues until the materials are all decayed or until the source of contamination is removed. And that's not always possible. For example, if a person is exposed to radioactive dust, then in theory, if it's on the skin, we can remove that contamination by washing the person down in a lot of water, a high pressure shower or a hose pipe. But if that person's also breathed in air containing that radioactive dust, then it's inside the lungs. And that is contamination we can't get rid of because you can't flush the lungs out, because that is a physical impossibility without damaging the person. Water and soils can also be contaminated. So contamination can spread into the food chain, because if the water and the soil has been contaminated, the plants living in the soil draw water from it, or if the soil's in it, they draw water that's passing through the soil, picking up that contamination into the plant, and then those plants are eaten by food sources for humans, such as animals, or even just by humans themselves. And at that point, it passes into the food chain, passes through to us. Contamination with radioactive materials with long half-lives poses a greater hazard than those with short, because the effects will last longer than for materials with shorter half-lives. So going back to our idea of contamination, looking at our young person there, if the radioactive emitter is emitting ionizing radiation, but that ionizing radiation is a particle that sticks to the person's body, as they move away, those particles are still on them, So they're contaminating the surroundings around them because they're carrying that source of radioactive emission with them. Radioactive material on skin or clothes keeps irradiating the person as their clothing is contaminated. And that is our final outcome. Explain the difference between contamination and irradiation. So I am going to stop there, and I'm going to say thank you again for watching. I hope that this was useful and helpful, and yeah, hope to see you again next time. Thank you.